Come on. There it goes. Okay, so today we're going to talk about diffusion in polymers, and I'm going to give you a variety of applications in which diffusion is important. And first off, for the ones we're familiar with, every time you go to the grocery store is packaging. If you go down the produce aisle, you see all this attractively packaged fruit and vegetables. All the greens are greens, the yellows are yellow, etc., etc. And a lot of that has to do with the packaging that they are encased in. Used to be everything was in a paper bag, and you had to look inside the paper bag. But now it's all laid out in front of us, and part of that is the fact that we have plastic wrap serving as a barrier, so that we can pick it up, look at it. We can't really touch it because the plastic wrap is in the way, which we're all very grateful for, so we don't pick up someone else's germs. But part of that is that engineering that plastic wrap. And so that plastic wrap has to be, obviously very clear. You can't have any kind of optical distortion, but it also has to have certain characteristics. And so we're trying to protect it from things associated with other humans, and we're also trying to protect it from potentially moisture, depending on what's inside that container. And we're also trying to protect it from other things in the environment: alcohols, formic acid, flies, anything, ants, anything that might get in there and decrease the production value of the fruit or vegetable. I forget what the stat is. That something like we grocery stores throw away like 30% of their produce because it starts to go bad. Some crazy number, crazy high number. Given how much production goes into it, it's really a crazy high number. But part of that involves this packaging, and so we want something that's clear, and we want something that's durable. We don't want something that shatters when you touch it. Okay, and there are 3 or 4 different testing techniques that are specific to these plastic films. There's a tear test, Elmendorf tear test, which I still remember, and a couple of other very specific tests that only relate to these plastic films. And that's how important this area is for plastic and plastic film technology. And so that's the one that we see the most of. We also have concerns regarding additives and what those can do to the diffusion coefficients of these different plastics. And that is particularly important when we talk about PVC pipe, which of course is almost more plasticizer than it is PVC. All right, so it's certainly very important here. We also think about gas separation. The one that is a big deal is separating carbon monoxide from carbon dioxide. There are certain plastic membranes that do that. It's a stack of membranes, and you start out with CO2, and then out the other end you get carbon monoxide and carbon dioxide totally separated from each other. And these are based on plastic membranes that have specificity, and that specificity is controlled by the structure of the plastic that goes into those membranes. We also think about chemistry, and this has to do with trying to sense things in some ways, have some type of reaction that takes place, and that has to allow for whatever it is you're trying to sense to get to what's inside the polymer. The one that always comes to mind, which I think is a myth, at one point I thought it was out there, they have these plastic strips they stick down your throat, and it touches your throat, and it's supposed to give you a visual on whether or not you actually have strep. Does anyone ever have that experience? Okay, some people, so they do exist now. Okay, for a while there, as people looked at me as like, what are you, crazy? But apparently they do exist. So some people have had this done. And so it's always been an issue in that you have sore throat. Is it strep or is it something else? Totally different treatment pathways, depending on what that is. Being able to find it out right there on site with the patient in front of you is very important. Monomer removal, for some examples of thermosets, dental thermosets in particular. So if you have a cavity, and no one ever has ever had a cavity in their entire lives, but if you do have a cavity, it has to be filled. All right, so you drill out that hole, and if it's a back tooth, they'll use amalgam, which contains mercury, which people don't like. They'll use gold, which is gold, but it doesn't look like the rest of your teeth, so sometimes people don't like that, although On chewing surfaces, they still use it anyway because it's better than the alternatives. If it's the front of your teeth, you don't want a piece of gold sitting there on an eye tooth or a piece of gray amalgam sitting there on the eye tooth, so they have white dental composites. All right, and those are this white paste that comes in a tube. They fill it a hole. There's also a substance that goes in the hole itself that helps bond the composite to the tooth structure. And then they hit that with a near UV light, a very bluish white light that's not UV because that could hurt your eyes, but it's close enough that it triggers the reaction of the TEG GMA and the BIS GMA, which are the two monomers that make up these composites, along with a bunch of nanoporous silica. And there's been a major concern about that because it turns out BIS GMA, if it diffuses out of the composites and you have enough of them in your mouth, there's a potential for it to change your gender. So that's something it is a minor concern. So it is surprising that in these thermosets you have any residual monomer left behind, but it is possible, and so that's been an area of concern. Polymer electrolytes are also important. We're trying to conduct electricity or allow ions to pass in polymers, and so diffusion there is important. Drug implants, so if you want to deliver something in vivo, deliver a drug via a capsule that's been implanted under your arm. We have a project working on horses where we're trying to deliver a drug to horses to keep them from making more horses because there's too many horses already out there in the western lands. So that's an implant made from a polymer through which these drugs have to somehow pass. And then biosensors is also a very, very big deal where we're trying to, we have a project on oxygen biosensors, and that's something that looks at diffusion of oxygen. We're also looking at glucose diffusion through polymers. So there's a huge number of areas where diffusion is important, from the mundane to the really high tech. And these involve a whole bunch of things. Moisture, plasticizers, dyes, worrying about whether those come out of plastics as we made them, different gases, ions, again, unreacted monomer ions, various pharmaceuticals. And this can be challenging because pharmaceuticals are not oxygen or nitrogen, and even glucose is pretty small compared to pharmaceuticals. And so the size of the molecule that has to diffuse, and that also holds for biomolecules, is very important. So we design these things to have various features that enable them to perform the goal, the application that we have in mind for them. All right, and so that can again range from hydrogen to things that are much larger than hydrogen. We'll talk about a lot of that today. All right, so these are aspects of diffusion, and in previous lectures we've talked about polymer chain behavior in the melt for polymers only, and polymer behavior in dilute solution, where the polymer is very much a minority component. Here the polymer, of course, is going to be the majority component, unless, of course, you have a lot of plasticizer in there, which changes things somewhat. And in this context, what can we predict about the motion of the solvent in this polymer? So a lot of the rules that we've talked about before spring up here as well. Like dissolves like is still important here, and we are interested in trying to figure out to the degree to which the solvent permeates the polymer. And we'll talk about what permeation actually means. Permeation and diffusion are not the same thing. Diffusion is a part of permeation, but permeation itself is the overall process. You guys have, with the inorganic side of things, they talked about Fick's law, right? All right, they've probably beaten that to death. All right, that's a small part of the overall process of actual permeation, which is something going in and actually coming out. Diffusion is just the passage part. How much is absorbed and how fast it can move through. Can it be delivered quickly? Can it be delivered slowly? Both things can be desirable. And in many cases, these are mainly amorphous structures. So for plastic wrap, why would that mainly need to be an amorphous structure? Oh, my watch is screwed up.
Because that way it's easier to bend and mold around whatever it is you're trying to cover with it.
It's more flexible. That's why we like plastic wrap. Any other things?
It's clear.
It's clear, we can see through it, right? Unlike some plastics, especially thicker ones. Anything else, sort of related to the first point, consumers tend to poke stuff, all right? So you go to the grocery store and you poke that plastic wrap, people just do it. We don't want the plastic wrap to shatter when it gets poked, okay? And so all these things are very important, and amorphous structures tend to give us that behavior. We can make a plastic film that is as thin as what you see in the grocery store and make it very highly crystalline, but if you poke that with your finger, it might just shatter. Your finger would go right through the film. All right. There are a lot of uses for rubbery polymers. Where is rubber important in terms of diffusion barrier? Typically, all over the place, used everywhere. Anybody know? You've probably seen them. Round, black things.
Tires.
What? No, not well. Tires is important, but even more high tech than tires. O-rings. All right. O-rings connect metal things together. All right. They allow gas to go through, and those O-rings have a very important role to play. If the O-rings fail, the space shuttle blows up. These are kind of important things, and so we were a lot about rubber polymers as diffusion barriers. Glassy polymers, things tend to be more complicated, as you'll see in a moment. And then we also have semi-crystalline polymers, crystallites embedded in the matrix. And we can engineer this to our benefit. It shouldn't surprise you that diffusion through an amorphous polymer is easier than it is through a crystalline polymer. All right, just off the top of your head, there's not much space in a crystalline polymer. All those chains are packed closer together. All right, it's more difficult for things to get between them. And this is another example of where we worry about diffusion. If we're packaging various drugs there in the cabinet, then we worry about how much water goes into them as a function of time, which typically determines the lifetime of the medication, after which it needs to be thrown out. And so things that we concern ourselves with are what are called sorption isotherms, which is how much a polymer can absorb into its structure. Diffusivity is a function of temperature. Typically this is why we don't store drugs over the oven, because we worry about the increase in temperature driving this change in diffusivity, which is then jeopardize the effectiveness of the medication. Solubility and diffusivity of various gases and polymers in natural rubber. Permeability of gases in natural rubber is a big deal. And then permeability of various gases in different polymers, which we're going to talk about here in just a second. But getting back to this structure, this is a heavily engineered piece of technology. There's a foil. Have you guys seen that? It's foil for a reason, because metal foils don't allow things to diffuse. All right, so we actually want that foil there. And then these structures, the plastic backing, those tend to be multi-layered plastic films, not just one plastic, but many different plastics, all of which are engineered to try to keep water out of these medications. So something today is actually pretty high tech. And so these are some examples of stuff that we have going on in the lab. We electrolyte particles, and ideally they're nice and round like that. That's not always the case. And we can put oxygen sensing, visual oxygen sensing compounds in those that tell us how much oxygen is in the system. We can also put drugs into these particles, which this is gabapentin, so this is used to treat spinal cord injury. So as opposed to being paralyzed for the rest of your life, you want the spinal cord to recover. So gabapentin is being looked at very closely to achieve that. And we have to look at trying to deliver those things into certain sites inside the human body. And ideally after injury, you can sort of see that little cut there. That's a spinal cord injury that they engineer in the lab. My colleague over in neuroscience does that on purpose, and we try to see how well the mouse can recover from those types of injuries. Is anybody feeling ill at this point after seeing these images? Some people really react badly to bloody images. I used to have a lab or in veterinary medicine, where we did a dog hip implant, and you never knew going into it who was going to faint watching this thing. It was surprising. Anyway, I'm sensitive to that, but I still show the images. Okay, so this process of diffusion is controlled by, as I said once before, is called a sorption isotherm, and this is essentially the polymer's inherent solubility for a substance, how much it likes this particular substance. And this varies a lot depending on the substance and the polymer, and I'm going to show you pretty much the worst case example of this, which is PMMA and CO2. And this is a subject for an entire field called supercritical fluids technology, which is used to make a lot of polymer foams, all right, which is useful. And this is showing you the solubility in cc's of CO2 versus cc's of polymer. And so you can see for this particular pair, we can get 9 cc's per cc of polymer. All right, so we started with it's 10 mils overall. 9 of those mils are polymer, are CO2, and the other 1 mil is the PMMA. All right, and so this is why this CO2 can be used to foam polymethyl methacrylate so effectively, because it has this enormous appetite for CO2. We don't see this in the inorganic side of things. We see a little bit of it when we think about palladium and some other things in hydrogen, but with polymers, this is part of the landscape. This is a worst case example where it can really go from being just 1 cc and expand to being 10 cc's by the time you finish stuffing it with CO2. All right. So this issue of inherent permeability is important. Question?
So 9 to 1 is naturally insanely high, but what's
it is
very, very low? Is there ever like a 0 per cc for?
For some polymer and permeant combinations, yes, there is. CO2 is under supercritical conditions or even subcritical conditions kind of thought to be a universal solvent for a lot of polymers, so it's really worst case. But other gases are nowhere near as bad as this. And what should also make some sense in this context, because of what we know, is that diffusivity drops with the penetrant size. We think about Stokes' law. And on the other hand, solubility will increase with penetrant size. And so this data shown here gives you some of this. And so you've got this fat dark line, which relates to what's on the left-hand axis, and the not-so-fat dark line, which relates to the right-hand axis. And there's this thing on the bottom which is called the Lennart-Jones diameter. Have you guys heard of Lennart-Jones before? We think about it in terms of, so you have seen some of this in terms of how atoms generally like to be around other atoms or not, and that's Lennart-Jones is important there. But this relates to the Lennart-Jones diameter of what is diffusing itself. And unsurprisingly, hydrogen, being, except for helium, kind of the smallest thing we worry about typically in terms of diffusion, we have a relatively high diffusion coefficient for hydrogen because it can fit through small spaces. This is true for polymers. This is also true for a variety of metals. The example I always like to give is the National Aerospace plane, which you guys have heard of that before, yes or no, maybe. Back in the 90s, they came up with this cool idea of taking a plane and powering it with hydrogen. It would take off from New Jersey and it would go through near-Earth orbit and land in Japan in 2 hours, as opposed to 18 hours, which is the current flight time to Japan. And what they wanted to do was to power this thing with hydrogen, and they couldn't use hydrogen gas because it takes up too much space. They wanted to use what's called slushy hydrogen, which is hydrogen that's so cold it's a slush of solid hydrogen, ice, I guess you'd say, and then liquid hydrogen. All right. They didn't want to use solid hydrogen because it's a big block of hydrogen which you can't pump very easily. But hydrogen slush was the planned fuel. And the problem they had with that is that when you go up and start burning this stuff, it heats up the metal. The metal becomes essentially transparent to hydrogen. So it was just kind of flowing out right through the metal like it wasn't even there. All right, because the metal's really hot, the lattice expands, hydrogen's really small. It's like it's completely transparent to hydrogen. So anyway, because hydrogen is so tiny, it does these kinds of crazy things. But then you go down to oxygen and the diameter increases, and very quickly that affects the diffusion coefficient. The other side of this is the solubility term, and this solubility can kind of be the inverse of diffusion. All right, and this is basically the ability of a certain material to hold on to something. And in the case of hydrogen, because it's so small, these materials don't tend to hold on to it because it leaks out so easily. Right? So that is great if you want things to diffuse. If you don't, it's a different matter entirely. But then as you increase the size of these things, you find that the solubility goes up. So PMMA has fantastic solubility for CO2 because it likes it. It wants to hold on to it. It won't let it go. All right, and so that in that particular context means you get a certain characteristic behavior. For PMMA, you put hydrogen in it, and the hydrogen kind of just goes right out once you put it in. So it's not going to swell PMMA very well because it just doesn't have any affinity for it. All right, and that all relates to the use of plastics in the grocery store as a barrier. Right, you want it to typically be a barrier to many things. Oxygen is not so much a big deal, but water and things larger than water we want it to act as a barrier. You want it to keep that diffusion from happening. All right, so how do we define these processes? And this is defined by permeation, which is the rate at which a gas or vapor passes through a polymer. And so we think about this in terms of three distinct processes. The one that we're all familiar with, because we talk about it a lot in inorganics, is diffusion. And that's kind of the middle process in this context. That's where we think about, in the case of metals, for example, we have vacancies, and these things diffuse through the vacancies and come out the other side. That's all well and good. But we also have, on either end of that, we have adsorption, and we also have desorption. And these help tell the whole story when it comes to permeation. If we have something that goes into a material and then it decides to, let's just not desorb. All right, so it goes in and diffuses like crazy and gets to the other side and it doesn't come out. The desorption part doesn't happen. All right, then we have permeation is zero at that point. So we can have fantastic diffusion but zero permeation. Right, so this is why we think about this big picture in terms of permeation, not so much diffusion, because those factors are all important. Conversely, if you have the adsorption process, if it refuses to adsorb, it doesn't matter how well it diffuses, it's also not going to go through it. Permeation is zero there as well. All right, so these surface-mediated processes have a lot to say about how good a diffusion barrier something is. Any questions about that? And part of that is we have difference between adsorption and absorption. Besides one letter, do we know what that means? D versus B. Yes? No? Yeah.
Is one like you have a force versus adsorption is there's no driving force. It's a natural.
Yeah, kinda. Yeah. So the process of adsorption is the gas arriving at the surface, and it can do a variety of things. It can go from being a diatomic molecule to two separate atoms, for example. That's one example of adsorption. And that process can be the force that you're talking about. It has to be forced into the surface, and that's the adsorption step. Absorption is not a surface-based process. Absorption is like a sponge. We take a sponge, we put water in the sponge, it absorbs the water into its structure. But part of that absorption process is what happens at the surface. If water beat it up on sponges, it's not going to go into the sponge. It doesn't matter how much the sponge likes it. The adsorption step is the key step, and those are two very different things. Adsorption is typically a surface-based process, and absorption is an internal-based process. So don't get those two confused. They are very different things. So we have absorption of the permeating species into the polymer. Diffusion occurs, and we'll talk about what that means in polymers. And then we have desorption of the remaining species from the polymer surface, accompanied by removal. And this is a great example of what that means in the context of plastics. So rather than thinking about these homogeneous metal blocks, we don't have to worry about this. We have to think about plastics, which have a lot of heterogeneity in them, along with whatever additives we might put in there, colorants, lubricants, fire retardants, all kinds of things. The polymer itself has a lot of heterogeneity. And so this is an example of a polyurethane film, which is famous in biomaterials. And these polyurethane films consist of both what are called hard and soft segments. And the hard ones tend to be something that has oxygen in it, for example, meaning that it can engage in hydrogen bonding. And the soft segment, on the other hand, tends to be more polyethylene-like. There might be some oxygens within the chain. And those two species, those two components of the polymer, have very different interactions with things that diffuse through them. So we can have gas molecules or we can have water molecules, And what we'll see on the high pressure side is this process of dissolution where it gets into the structure, and then the diffusion, which has two components to it, which is interaction with the hard segment, and then we also have interaction with the soft segment. All right, and both of these can contribute to the diffusion of whatever it is through these polyurethane plastics. All right, and so it's not just one thing. We always think about metals and diffusion in metals, and that's typically just one thing. But in the context of plastics, we have a variety of things that can interact with them. And this is just one of the more extreme examples where we have hard and soft segments. If we have a copolymer, all right, that's another example of something that can have an affinity for water versus lack of affinity for water. And overall, that net affinity is what controls permeation. Does that make sense? Okay. We can think about permeability. We can define it quantitatively, which, as you may be familiar with, chemical engineers kind of speak a different language than we do. And this is where this starts to show up because it's primarily a chemical engineering term. P is equal to the volume of vapor passing through unit area of polymer per unit time with a unit pressure difference. And key part of that is this pressure difference. So the pressure drop that occurs across the film, that is the driver for these processes. If the pressure drop is zero, then there's no driving force. And this is something that we're kind of familiar with in terms of diffusion, but here we're typically talking about gases. So permeability is equal to the quantity of permeant times a film thickness divided by area and time, which is something we see. And again, driven by this pressure drop. The solubility coefficient, the volume of vapor per unit volume of polymer versus unit pressure. Units of permeant is centimeters cubed times centimeters divided by centimeters squared divided by seconds divided by pascals, none of which we're very familiar with as materials engineers. The units of solubility are centimeters cubed divided by centimeters cubed divided by pascals. Again, something that doesn't really make sense to us, but this is a consequence of the fact that we're talking about gases. The diffusion coefficient is centimeters squared per second, which at least makes a little bit of sense to us. All right. And so we're used to seeing things like that, but these other units don't have a lot of familiarity to us. And so the permeability in polymers at 25 degrees C is given by this table, and it talks about the polymer, it talks about the permeant, what is diffusing through, it talks about the permeability times 10 to the 13th, so that it produces a relatively easily ranked set of numbers that we can look at. And then we have this reference permeability at 10 to the minus 7th, which connects to Arrhenius equations, which we should all be familiar with. You guys, are you still forced to do an Arrhenius coefficient determination in lab? Okay, yay! So you're used to that. And that is also familiar in that there's always an activation energy here. All right, so with inorganics, that activation energy is how easily a vacancy can exchange with a neighboring additive. All right. In this context, we have the same type of relationship, but rather than having a three-dimensional crystalline lattice and vacancies, we have polymer chains, which are not a lattice, all right? They're not rigidly held. And in the context of diffusion with polymers, we're usually talking about the ability of the polymer chains to get out of the way. That's really what it boils down to. We don't have a fixed concentration of vacancies so much, although what we do have is this issue of the free volume, all right? And we think about that and how easily that enables chains to get out of the way. So it's kind of a similar thing, but they're not defined structural features like vacancies are. And so we have a couple of very important additions here. Low-density polyethylene, which is typically what you see in the grocery store nowadays. Used to be the Saran wrap was made out of polyvinylidene chloride, as it says here, major component of Saran wrap. Turns out that's not the case anymore. Why did we go away from polyvinylidene chloride? Anybody know? Yeah.
You place it in the microwave, the chlorine can gas out and get hot enough temperature.
You can get some chlorine gas from it. That would be a pretty extreme condition. You don't normally heat it up that much. Any other? Yeah.
Did it cause cancer in California?
Well, everything causes cancer in California, but where specifically was it causing cancer? Not necessarily right there in the grocery store or right there in your microwave.
Stomach.
What?
Stomach cancer?
Oh, well, if you ate it, maybe you might have that issue. But the key was that what happens in the waste stream. All right, when we're all said and done, we're done with our saran wrap, we wad it up, put it in the trash can. It's not going to be recycled because it's number 4. Number 4 does not get recycled. All right, regardless of this fantasy we have in the recycling bin, it doesn't get recycled. I think Kroger's can take them and maybe they'll make more plastic bags out of it. Generally, it doesn't get recycled. What would happen in the case of the old saran wrap, it would not get recycled. It goes in the trash, it gets incinerated. All right, and in the incineration process, you've now introduced chlorine. And what that would do is it would interact with all the other stuff like PET in particular and produce dioxins. And dioxins are really bad things that do cause cancer. Okay, and the other bad thing about them is they don't break down. They'd come out of the incinerator, they'd settle on the foliage, and they'd settle into streams, and sunlight would hit them and so forth, and oxygen and water would be around, they just sit there. All right, the dioxins are very stable. They are also very carcinogenic. And so we got rid of that, at least in terms of chlorine, and replaced it with LDPE. But we can look at the relative interactions of these things with permeants. We think about water, we think about nitrogen, not so much an issue in terms of food. Oxygen, of course, can oxidize the flavor compounds in your food and so forth. CO2 is something of an issue because with some fruits and vegetables, especially I believe it's tomatoes, they are very sensitive in terms of their ripening. And then water, of course, is part of what causes rot in vegetables. And so for these different species with these different films, you can see that we did make a bit of a trade. Nitrogen, oxygen, CO2. In the old saran wrap, they would not diffuse as easily as they do in the new saran wrap. Not that we've noticed so much in terms of its ability to protect food. But so there was some trade-off associated with that. Other things, other areas where we're still looking at this, and this is polyethylene terephthalate, which is important because it's used where? Pop bottles, right, all right, which have CO2, all right? And so we worry about whether or not our CO2 can escape out of the pop bottle and it goes flat, all right? End of the world if your soft drink is not fizzy, okay? And so these are the things that we worry about in the context of working with these different types of plastics. Any questions about this? All right. Main factors affecting the permeability of polymer: the solubility and diffusivity of the small molecule in the polymer, chain packing, side group complexity, polarity, crystallinity, orientation. Fillers are very important. We can do things with plastics, not so much for plastic wrap in the grocery store, but other areas we can put clay into it. All right. So in this context, clay not only makes it cheaper, but it also a great barrier to diffusion. Clay particles are very good at preventing diffusion. Humidity is significant. If we load up a plastic with water, it doesn't necessarily act in the same way when it comes to diffusing CO2 in particular. And of course, plasticization, where we have a lot of plasticizers in these systems, and then it's not so much the affinity of the PVC for whatever's diffusing, it's the affinity of the DEHP for whatever's diffusing. One example, from the literature, you can take plastic film, and what they were doing was they would nucleate and grow plastic crystals that were growing parallel to the direction of the film, and so when it came time for something to diffuse through, it would run into those polymer crystals, and that would help reduce the permeation, reduce the diffusion of pretty much anything, water, CO2, oxygen, through these plastics by generating polymer crystals that get in the way of that diffusion because it's a more tightly packed structure. All right, so for a certain area of application, it is useful. Not so much in the grocery store, again, because we could poke that with our finger and it might shatter because of those same crystals. But in other areas where that's not a threat, this is an effective strategy for moderating diffusion. Okay, so the key aspect of this that makes these materials very different from what you're used to is the motivating forces available to us. So I'll start with this example. Continuous pathways through the polymer. We talk about inorganic diffusion as a relevant point of comparison. And so we have, of course, a vacancy, all right? And then we have atoms that exchange with that vacancy and start moving around in the context of these structures, and they start jumping back and forth. And this is one of the reasons why vacancies are so important in the context of inorganic diffusion. Vacancies are what allow for diffusion to take place, except for things like hydrogen. Most diffusion species in inorganics rely on this process of vacancies being available. Vacancy concentration, is it constant or does it change with temperature? Which what?
Changes with temperature.
Temperature with temperature. Okay, so as we increase the temperature, the number of vacancies go up, diffusion increases, which is why hydrogen flies right through the spaceplane engine walls, because it's gotten so hot and there's so many vacancies present that diffusion is relatively easy, because those vacancies are providing this pathway for this process to occur. And in these inorganics, eventually everything exchanges position. We start out with a defined color on one side, defined color on the other side, and all this exchange driven by these vacancies has helped randomize that structure as a function of time. In plastics, however, we don't have any of that. Okay? What we do have is free volume. And in that context, we think about free volume as providing holes, and those holes are basically the ability for polymer chains to get out of the way. And so we describe this with inorganics, though, in an expression you should be used to seeing. The flux is equal to the negative of the diffusion coefficient times the partial of concentration with respect to distance. And so we see this as this classic view in which D describes this diffusion coefficient. And the change in concentration is going to be affected by D. How steep that factor is, how large the diffusion coefficient is, determines how quickly that process takes place. However, for polymers, and this just makes it clear this is inorganics. For polymers, things are nowhere near as tightly defined, and it actually does make some sense given what we know about them. We have the change in concentration with respect to time is equal to the partial with respect to distance of the term, the diffusion coefficient. All right, so what that says is the diffusion coefficient depends on where you are inside the plastic. It's not a constant like it is in the metal. And we also have the change in concentration as a function of distance. J, as before, is the flux of the permeant. D is diffusivity. For the polymer, this is depending on the polymer itself, how much it likes what's diffusing through this, the diffusing species, the temperature, of course, and in some cases on the concentration C. And so what that is, in the majority of cases, the concentration of what is diffusing can affect the diffusion coefficient. All right, that's why this expression exists, because D is not a constant in these systems. And hopefully that makes some sense based on what I showed you a few minutes ago. We talked about PMMA, how much it loves CO2. All right, at 9 cc's per cc of PMMA, it is not just a solid matrix of PMMA anymore. It's this weird blend of CO2 and PMMA. And so that the diffusion coefficient of that structure is nowhere near what it would be for just pure PMMA alone. And so what that means is what is diffusing can trigger additional diffusion. Okay? Hopefully that makes some sense. Again, thinking about that very extreme example. The diffusion rate unsurprisingly, decreases the permeant size. For LDPE, we saw this before. The size of the permeant drives down very quickly the permeability in these systems. Even small differences in the size make big differences in the diffusion. This is showing you a bunch of data for, first off, relatively small things that can diffuse through plastics pretty well, including the films in the grocery store. However, as we get larger, we look at things that we don't want to diffuse through the plastic film in the grocery store, because they can definitely affect the quality of whatever it is we're working with. And so small changes in diameter result in big changes in permeability. All right, rubbery polymers give us ideal diffusion behavior. All right, it's called Henryan diffusion behavior, which is shown here, in which this concentration is linearly dependent on pressure. You guys should have seen this in physics, Henryan solids and Henryan diffusion. Yes, no, maybe. Okay, maybe not. All right.
It's been a long time.
It's been, oh, come on, it was just last week. Glassy polymers, on the other hand, these have anomalous behavior via what are called dual mode absorption mechanisms. And what that means is we have adsorption into what are called microvoids, holes, but you guys just think about it as free volume. And the issue is, which if you think about it should make sense now, is that the species that is diffusing, we spent a lot of time talking about, affects the free volume itself. You just had a test question about that. So you bring in something into the polymer, it affects the free volume, which affects the ability of the polymer chains to move around, which affects their ability to absorb more of that stuff that's going into the plastic. All right, so there's a self-catalyzing effect that gives you a nonlinear behavior, and that's what's called Langmuir adsorption, in which it starts not as a linear relationship, but it builds and eventually reaches some plateau based on the affinity of that plastic for whatever it is that's coming into it. All right, it will get to a constant level, but initially it's not linear at all. All right, it's a nonlinear process giving rise to nonlinear changes in diffusion. And as we talked about before, the microvoids is a free volume frozen into the structure at the glass transition, whatever that might be. We know that it goes from these two conditions, as glassy to more of a liquid type of mechanical property, and that TG is very important. And it should make sense that TG is important because that's where the chains move away from each other. Below TG, you don't have a lot of sensitivity there because it's hard for the chains to move around. All right, below TG, it's this frozen-ish amorphous structure. Above that, it's not so frozen. It's still amorphous, but the polymer chains can move around a lot more easily. Solubility is given by the enthalpy dissolution, delta H sub S. Above TG, endothermic chain separation. Below TG, exothermic heat of absorption. Very different behaviors as far as diffusion between these two conditions. And that should make sense to you, given what we know about glass transition. Right? We're not at 0 degrees Kelvin, but we took away a lot of the energy and a lot of the space between these polymer chains. And unsurprisingly, this is an energy-activated process. Arrhenius behavior works here, although when we think about inorganics, that's basically the vacancy in the atom changing places. Here, think of it in terms of a polymer chain moving out of the way of what needs to diffuse. Right? Much less defined in terms of structural changes involved, but that's essentially what we're looking at. The effect of the glass transition gives rise to changes in slope. For a rubber, we have a very different energy of activation than we do for a glassy structure. For a rubber, the permeant must create channels, activate channels. For these glassy structure, the penetrant moves through local holes and local activation. And so this is significant for rubber because, as I said, that's how O-rings are designed, is working with this channel creation, whereas most thermoplastics, it's moving through these holes and achieving local activation. Okay, contrast. It's not inorganic diffusion. Inorganic diffusion is movement through vacancies and sometimes interstitials. Vacancies is easier to understand, but interstitials can also be important. Plastic diffusion, on the other hand, is passage through voids or gaps between polymer chains. All right, and hopefully that screams free volume to you at this point. That's what's at work here, is free volume. Above the glass transition, which is typically where we operate when we have these plastic films, the amorphous polymer has considerable free volume, high chain mobility. The chain segments can easily move out of the way of whatever it is that's diffusing and cause this process to occur, and this gives rise to relatively high values of diffusivity. Of course, this is also governed by how much that chain likes whatever is trying to diffuse through it. All right, it's possible that could drive things the other way if there's enough of an affinity for that diffusion species. Below the glass transition, we still have the amorphous polymer. That hasn't changed. Clear on that, I hope. Much less free volume, low chain mobility. Diffusion paths are more tortuous, which is a kind of a dramatic word to describe the problems that are associated with this structure. Low diffusivity, and that's all well and good. So compared to being above the TG, that should all make sense. But where things get interesting, and this relates back to this self-catalysis effect, we can be, if our conditions are we have an amorphous polymer and we are at the glass transition, these diffusing molecules can do what we now know they can do. They can increase the amount of free volume present in the system, and that can effectively lower the glass transition. So we have a situation in which what's diffusing causes it to go through the glass transition and triggers enhanced diffusion. And this is one of the primary reasons why Fick's law no longer applies, because this kind of stuff can happen. Question?
Could the opposite be true of this for the above the TG, where it would kind of slow diffusion even further? Tighten
the only way that can happen is if there's a real affinity between the diffusing species and the polymer chain. And in most cases, what's diffusing is a molecule or even a gas, and it's just not going to gum things up like that. I mean, if it was a really large compound, maybe that could happen. But in general, what we're talking about for most applications is a small molecule or even a gas. And so it's just going to increase the free volume even more, give it more room to move around and vibrate. Any other questions? All right, so the presence of the permeant modifies the properties of the polymer and drives this change, this nonlinear change in the diffusion coefficient, which makes plastics very different from metals. All right, so essentially acts as a swelling agent for the polymer. When that polymer contains groups that like or interact with the penetrant groups, gives you a feedback loop for swelling and solubility. Adsorption can become nonlinear under these circumstances, and this is how we see things like PMMA sucking up a lot of CO2. In contrast, however, crystalline regions are almost always impermeable. Diffusion, when it occurs, is going to happen through the amorphous regions between the lamella. All right, so these are really great barriers for diffusion because they are so closely packed. But as we've understand now about plastics, we don't have giant single crystals. All right, we always have amorphous components, even if it's just a fold surface, and we can have diffusion in those amorphous areas. It slows things down because it's a much more indirect pathway through the crystalline structure than just going straight through the amorphous chains. But because there's always an amorphous component present, you're always going to get that level of diffusion. But it's not really going through the crystalline regions at all. It's going around them. Okay? Any questions about that? Did everyone look at the video in preparation for today's concept test? All right, good. Again, as I've said before, I've done it in previous tests, which you'll see when I post them. I can take pictures right out of that video and ask you questions. So we'll demonstrate your abilities on Friday in this area. All right, see you then.